Cast is now starting. All attendees are in listen-only mode.
Hello, and welcome to our webinar, Advanced Analytics for Chemical and Petrochemical Organizations with Swan Black and Seeq. Thank you for joining us. A few things to mention before we begin. Please submit your questions through the questions section of the GoToWebinar console. If we do not answer your question during the session, we will follow up with you afterwards. For additional questions, please email Joseph Gardner at swanblack.com. Our presenters for today's webinar are Joseph Gardner, Practice Lead at Swan Black, and Nicholas Gagliotti, Seeq Analytics Engineer. And with that, I will hand it over to Joseph.
Okay, great. Thanks, Lisa. Good morning, everyone. Thank you to all who are joining us. Appreciate everybody taking a little time out of their schedule. A little bit about myself. I'm Joe Gardner. I lead our advanced analytics practice called Swan Black. Swan Black is an operating affiliate of GS Systems, who has served the industrial manufacturing industry for over 25 years. We have extensive experience working with customers in the chemicals, life sciences, food and beverage, power, and CPG industry verticals. By background, I have a master's degree from the Kelley School of Business at Indiana in business analytics, and have spent most of my career working in a consulting capacity, helping customers generate meaningful insights from their process disparate data sources. For those who haven't heard or worked with us in the past, Swan Black is an advanced analytics practice that helps accelerate time to insight for process manufacturers. Our partnership with Seeq is a means for interacting with our customers and empowering them to make decisions based on insight rather than intuition. We're a Seeq certified partner with Seeq certified analytics engineers on staff. Basically, what this means is that we've gone through the Seeq certification process to be able to provide the highest level of service to our customers through Seeq. We see the need for chemical production facilities to be able to evolve and respond to changes in regulations, energy costs, and raw materials. It is important that process engineers be able to perform root cause analysis to generate, share, and collaborate process data insights that help improve production outcomes. Today, we'll showcase some sample use cases that can help chemical manufacturers improve these production outcomes with advanced analytics. And Nick, I'm going to pass it over to you. So just for everybody's benefit, I will circle back at the end with questions. If you have any questions for me or about our practice, happy to answer anything you have. So Nick, I'll kick it over to you.
Thank you, Joe, and good day, everyone. My name is Nick Gelati. I'm an analytics engineer with Seeq. As an analytics engineer, I assist our customers developing use cases. I develop best practices for solving specific industrial problems in Seeq, and I train our customers in the use of our software so that they are able to drive maximum business value from their work. I'll start by giving a brief introduction of the capability of Seeq and our product's architecture. Then I'll present several use cases we've built out with our customers. The first is a batch tracking and cycle time analysis use case. The second is a product properties prediction based on upstream process conditions. And the final one is a predictive analytics for maintenance use case. I'll start with Seeq's product architecture. Seeq connects to many different data sources. Process historians like OSI Soft, Pi, and Wonderware, where your manufacturing data from production plants might be stored. SQL-based data sources, and any custom data sources where you might have maintenance data or lab data. All of those different data sources are indexed by the Seeq server, which can sit either on-premise or in the cloud. Users can access this data from any modern browser in several different Seeq applications. Most of the data analysis is done in Seeq Workbench, where the user trends signals, contextualizes their data, and cleans their data. Once a user has built several analyses in Workbench, they can combine them all together in the Seeq Organizer, a reporting and dashboarding application that they can use to share their work with others. If the user wants to do more advanced calculations and visualizations using Python, they can use Seeq Data Lab. Here, they'll use Python libraries to run more advanced algorithms with the data they've pulled from Seeq. They can then push new signals from Data Lab back into Seeq Workbench or push custom visualizations into Organizer topics. Seeq helps engineers to rapidly perform many different types of analytics. They can use point-and-click tools to identify past upset events for diagnostics and root cause analysis. Predictive modeling tools allow users to create soft sensors or virtual models of signals to monitor if processes are running as expected. These analyses can be combined into organizer topics to prepare summary reports and dashboards, or data can be pushed into Seeq Data Lab to develop more complex algorithms. And with that, I'll jump into our use cases. The first use case we will review today is a batch cycle time analysis that we performed with one of our customers. This customer was attempting to decrease the overall cycle time of their batch process by eliminating idle time during the batch and reducing time between batches. The typical techniques they used to perform batch cycle time analysis with spreadsheets was extremely time-consuming. It was very difficult for them to accurately identify each phase of the batch, as they frequently had to double-check that they correctly identified each batch phase by cross-referencing with their process historian. In addition, they were limited by the mathematical operators available in spreadsheets, so it was difficult to identify complex phase start and stop times. Finally, it was very tedious to scale their analysis to all batches in time. With Seeq, we easily identify each phase of the batch process using point-and-click tools and use Seeq formula to calculate more complex items like derivatives. As we define phases for one batch, the calculations scale out to all other batches automatically. Performing the batch cycle time analysis in Seeq for this customer took significantly less time than with spreadsheets, allowing the engineers to focus on implementing process improvements instead of wrangling data in spreadsheets. In addition, they were able to shave several minutes off of the batch cycle time by eliminating idle time within the batch and time between batches, and reducing time between batches, which ended up resulting in a $2 million production increase annually. With that, we'll dive into a demonstration. So in this example, the customer was performing a batch cycle time analysis on their polymerization reaction step, in which catalyst is added to the reactor to polymerize monomers. For this example, we used 3 process signals, which are shown on the screen here. A batch reactor level signal, the catalyst feed rate signal, and the reactor temperature. This unit operation had several steps which we wanted to identify. A pump-in phase, where material is pumped into the reactor. A temperature ramp phase, where the reactor temperature is increased to the polymerization temperature set point. A catalyst addition phase, where catalyst is added to the reactor to polymerize monomers. And finally, a pump out phase, where material is emptied from the reactor. There's also idle time during the batch, which is any time one of the non-value adding steps that we mentioned is taking place, as well as time between batches. So the goal of analysis is to capture all of those different phases and try to see if there are any patterns in when the idle time phase is occurring, so that we can implement process control improvements to eliminate idle time. We'll use the Seeq tools shown here to complete our analysis, and we'll also use the Seeq journal to step through the different steps. The first step in our analysis is to identify when a batch is being produced. For this, we'll use the value search tool and look for where the batch reactor level signal is greater than 0.5 for at least 20 minutes. You can see on the right side of the screen that I've got some green bars representing when batches are being produced. These green bars are called capsules. Next, we'll identify the pump in and pump out phases. You can see that my batch reactor level signal is quite noisy. Before we do any additional calculation on it, we'll apply a low pass filter to smooth out some of the measurement noise which occurs due to the reactor's agitator. To create the smooth reactor level signal, we apply a low pass filter with a cutoff of 20 minutes. Next, we'll calculate the derivative of the smooth reactor level signal. To calculate the derivative, we can use Seeq formula and apply the derivative function. Now you can see in the fourth line of the screen, we've got a signal that represents the derivative of that smooth signal. If we had not applied the smoothing algorithm, that derivative would be extremely noisy. Next, we can use value search again to find the pump in times. This is where the derivative is greater than 0.01. Similarly, to find the pump out times, we can apply another value search to find where the derivative is less than negative 0.01. So now you can see that we've got 3 sets of capsules on the right side of the screen. We've got capsules for the pump in times, the pump out times, and then the overarching batch condition. The next step is to identify the catalyst addition times. Again, we'll use a simple value search to identify when the catalyst feed rate is greater than 0 for at least 10 minutes. And you can see that we've got capsules for the catalyst addition times now. Finally, we need to identify the temperature ramp times. Similarly to the batch reactor level signal, the batch reactor temperature signal is quite noisy. Before we do any calculations on it, we'll apply another low pass filter to the temperature signal to smooth it out. And for this, we use the low pass filter tool in the tools panel. And like we did when we identified the pump in and pump out times, we'll calculate the derivative of the smooth temperature signal. And again, we can use value search to find when the temperature is increasing by finding when that smooth derivative signal is greater than 0. You can see that we've got some capsules for each batch for the temperature increasing periods, but sometimes they overlap with the catalyst addition capsules. This is because the temperature of our reaction mixture increases as catalyst is being added to the reactor because this is an exothermic reaction. So what we really would like to do is capture the periods when the temperature is increasing, but catalyst is not being added to the reactor. To create a condition that's a combination of 2 other conditions, we'll use the composite condition tool to find when their temperature is increasing minus when catalyst is being added. Now we've successfully identified all the value adding steps of our process: a pump in time, temperature ramp, catalyst addition, and pump out. We're ready to identify the idle time, which is any time during the batch when one of these value adding conditions is not present. To find these times, we'll use Seeq formula again. We'll look at our overarching batches condition and subtract from that the pump out time, the pump in time, the heat up, and the catalyst addition conditions. And you can see that we're left with tiny capsules during each batch, which represent that idle time. And you can see that that idle time sort of took place between the catalyst addition phase and the pump out phase for almost all of our batches. So that was the pattern that the engineers were looking for when they set out to do this batch cycle time analysis. Oops. Now that they've found where the idle time occurs in most batches, they can implement process control changes to reduce that idle time. The last step will be to identify the time between batches. And for this, we simply took our batches condition and applied the inverse function to it. The inverse function creates a condition that is the inverse of other capsules in the condition. So with a couple of point and click tools and some simple Seeq formulas, this customer was able to identify all the value adding phases of a process and found that most of the idle time occurs between the catalyst addition step and the pump out step. Then our customer's engineers implemented a control sequence change to ensure that the pump out phase started as soon as the catalyst addition ended. This shaved off several minutes in each cycle that amounted to a $2 million production increase over the entire year. So with that, are there any questions about the first use case?
We do have a few questions right now, and again, you can submit your questions through the questions section of the GoToWebinar console. First question, I have defined my batches and batch phases using Pi event frames. Can I use these in Seeq?
Yes, so we have a connector to Pi as a framework where we can import Pi event frames from, and you can use those event frames. They'll show up as conditions and capsules. You'll be able to do any of the sort of analytics I showed with those event frames.
Great, thank you. The next question, if I make a small change to parameters of one of my batch phases, will that change propagate through the analysis and change the other conditions derived from that phase?
Yes, so if I made a change to one of my value searches that identified, say, pump in or pump out, that change would not only affect the pump in and pump out capsules, but it would also affect any capsules that depended on the pump out and pump in phase. So my idle time condition would change, for example. My time between batches might change as well. And that change would be applied over all batches in history, not just the ones that are shown on the screen.
Excellent, thank you. And the last question we'll get to in this section, how can I scale my analysis out to other batches in history?
So when you apply a calculation to and build conditions for the data that's shown in the display, scaling that analysis out to other batches from other times is as easy as just moving your time range to a different period in time. So all we would have to do is change our display so we show some other period of time, and those calculations would be applied for that period of time as well. It's very easy to scale your analysis.
Thanks, Nick. We will have another section for questions at the end, but for now, we can continue with the use cases.
Okay. Next, we'll review a use case in which a customer used Seeq to generate a live product quality model using several different input process variables. As you may know, controlling finished product properties is critical for maximizing production quality and, as a result, profitability. The majorities of companies in the chemical industry control finished product properties based on feedback from lab results received some hours after the material was produced. In Seeq, we reliably and accurately can forecast product properties based on conditions in an upstream portion of the process. This allows the customer to make real-time process adjustments instead of waiting on lab results, and minimize significant margin loss associated with product downgrades. We'll jump into the use case. So in this example, we're going to build a model of our product quality signal using several input process variables. So those input variables are the modifier flow, reactor temperature, reactor conversion, and then the product quality that we're trying to predict is the product viscosity. And also we have a grade code that indicates which grade is being produced. So we'll start by zooming in on one of our grade transitions. You can see that when the grade changes, you see an immediate corresponding change in the process variables as the operators adjust parameters for the new production run. However, there is some delay in analyzing the first quality sample, so the viscosity signal doesn't change for some time after that grade change. For this process, that delay is about 1.5 hours. So the first step in our analysis will be to generate a new viscosity signal that changes when the grade changes. For this, we'll use Seeq formula and apply the delay function to that raw viscosity signal. This function will move the timestamp of the viscosity signal backwards in time by 1.5 hours. You'll see that the delayed viscosity signal now aligns with the process variables as they change due to the grade change. Next, we'll apply some smoothing algorithms to our input signals, as we do not want to include excessive signal noise in the viscosity model, which we will do shortly. For this example, we're using an agile filter instead of the low pass filter that we showed in the last example. This is because the agile filter is a filter that works better close to now. And as we'll use this for monitoring the process near real time, we want the best filter for real-time smoothing. The next step will be to generate our viscosity model. For this, we'll use the prediction tool, and we'll be modeling the delayed viscosity signal using the smooth process variable signals as inputs. We define a training window as the first quarter of this year when the process was operating normally, and we've chose a simple linear scale for this model. In addition, we're using ordinary least squares regression. And scrolling down to the prediction model section, you can see that this model has a very good R-squared of 0.94. However, we can also evaluate the goodness of fit in our model by using the scatter plot tool. And for this scatter plot, I'm plotting the delayed viscosity, so the raw signal on the x-axis, and the predicted viscosity on the y-axis. So you can see that there's sort of binning for each grade, but in general, the delayed viscosity and predicted viscosity are pretty well aligned. Now we're ready to generate a monitoring view so that our engineers and operators can make real-time process adjustments using the predicted viscosity signal. To do this, we've just applied some boundaries to our predicted viscosity signal. The upper and lower bounds being the upper and lower specification limits for our product viscosity. You can see that the specification limits change as the grade changes. Then, as a final monitoring view, we'd like to use this model in near real time. So we've got the viscosity model shown in the top lane and the process variable signals shown in the bottom three. So the engineers can use this new view to make changes to their process in real time. One additional useful view is the presentation mode view. This shows the Seeq dashboard without any of the underlying Seeq content around it. And as new data comes into Seeq from the plant, this presentation mode view will change and move with new data. Okay, so we'll move on to our final use case for the webinar. This last use case we'll review is a heat exchanger maintenance prediction use case. So predicting end of cycle for a heat exchanger due to fouling is a constant challenge faced by the chemicals industry. Proactively predicting when a heat exchanger needs to be cleaned enables risk-based maintenance planning and optimization of processing rates, operating costs, and maintenance costs. Before using Seeq, engineers had to manually combine data entries in a spreadsheet and spend days or hours formatting and filtering the content or removing irrelevant data when necessary. For example, when the equipment was out of service. Utilizing the Seeq formula tool, we can monitor heat exchanger performance in place of the time-consuming spreadsheets, eliminating weeks of work for engineers, freeing them up to perform other valuable tasks. Millions of dollars could be saved per year as a result of improved turnaround planning and other improvement opportunities. Operational plans can be optimized based on heat exchanger performance, and planned maintenance costs can be minimized. With that, we'll jump into the demo. There are three major steps associated with this analysis. On the left, you can see three worksheets, one for each major step. I'll use Seeq's journal feature to navigate through each of these steps. The first major step is to collect the process data signals required to do this analysis. In the first lane, I have two flow rates, the hot side and the cold side flow rates in pounds per hour. In the second lane are the cold liquid inlet and outlet temperatures. Similarly, in the third lane, I have the hot liquid inlet and outlet temperatures. So in total, I have 6 process signals that I will be using for this analysis. I'll click on the second worksheet to begin the second major step, where I will calculate all of the additional derived signals from the 6 inputs. Beginning in the same view as in the first step, the first set of derived signals I will calculate are the hot, cold, and average heat exchange duties. Here I can see in units of 1,000,000 BTUs per hour, the cold duty, hot duty, and average duty. I'll click on the edit button to the left of the hot duty to see the formula that I've used. And for this, I've used the first principles relationship of Q equals M times CP times delta T. And you can see the formulas, the functions used in that formula box. The next set of calculations is the hot approach and cold approach temperature deltas. From those approaches, I will calculate the log mean temperature difference, or the LMTD. If I click on the edit button, you can see the formula I used to calculate the LMTD. Now I can calculate the heat transfer coefficient from the calculated LMTD and the average fluid heat duty. You can see the formula that I've used to calculate U. In this equation, I know Q, the duty, A, the surface area, which is a constant, and I just calculated the LMTD. In addition, you notice that I've applied data cleansing to this analysis through use of the remove function. The remove function will remove periods of bad data. In this case, the bad data is the large downward spikes that result from things like short downtime periods. These periods of bad data were identified prior to the analysis and could be flagged in several ways by using value searches like I did before, by using maintenance logs, or by manual selection from the user. I've also created a normalized heat transfer coefficient. If I edit the normalized signal, you can see that I'm using the actual liquid flow and a designed constant hot liquid flow to normalize the heat transfer coefficient for this analysis. If I I'm also removing data like I did for the normal heat transfer coefficient. The last items I will add to the analysis are two scalars. The first represents the design heat transfer coefficient for this heat exchanger. And the second is the minimum heat transfer coefficient required for optimal analyses. You can see that the design limit is 100 BTUs, and the minimum operable heat transfer coefficient is 30 BTUs. So you can see that my heat transfer coefficient degrades over time, and what I'd like to do is find when that heat transfer coefficient goes below my lower threshold. And to do that, we'll use the prediction tool like we did in the predicting product properties use case. I'll add the current heat exchanger cycle condition to the display. This represents the time period representing the current operating cycle. The start of this heat exchanger cycle was on November 1st, 2015. I'll choose an end date that is sometime in the future sometime after this heat exchanger will go below the minimum operable design limit. You can see the purple bar representing the capsule for the current heat exchanger cycle. Next, I will create an accumulating counter to represent the accumulated days that this heat exchanger has been in service during the current cycle. To accomplish that, I create a series with a value of 1 and integrate it over the current heat exchanger cycle, and then convert units to days. You can see the resulting days in service counter increasing in time. The next step is to create a prediction of the heat exchange coefficient as a function of the days in service accumulator that we just generated. We see here that I have selected the normalized heat transfer coefficient to model, and as an input signal, I use the days in service counter that I just created. Optionally, I could select additional inputs relevant to the system, such as dissolved solids, to further refine my model. I'm using a linear prediction. I could select other options if my degradation had a different trajectory, and I have an R² of 0.96. You can see the resulting prediction as a dashed line that's slowly decreasing towards my minimum operable heat transfer coefficient. The final step is identifying when the predicted failure or required maintenance will be, based on the data in the prediction. Where my predicted heat transfer coefficient intersects the minimum operable heat transfer coefficient, represents the projected failure date. I'll mark this spot and see that I'm expecting the heat exchanger to fail in the second half of August 2018. I can now communicate this analysis to the maintenance department and work with them to schedule a maintenance outage to clean this exchanger prior to that failure date and prior to it becoming an operating constraint for my unit that would result in cutting rate or other operational issues. So that concludes the use case presentation. Are there any additional questions?
Yes, we do have a few additional questions right now. And again, you can submit your questions through the questions section of the GoToWebinar panel. First question, is it possible to receive a notification for when I need to perform maintenance on the exchanger?
So notifications are future Seeq is working on implementing in the future, but we can also integrate with Pi notifications to give you a notification of when the predicted exchanger, the predicted crossing of that minimum operable heat exchange coefficient will occur.
Okay, the next question. In the predicting product properties example, if the residence time of my process is constantly changing, can we use that residence time to delay my signals?
Yes, so with the delay function, you can delay one signal by another signal. So if we could generate a new signal that represented the residence time of my process, I could use that as input to the delay function instead of the scalar that I used in this example.
Great. I think this will be the last question we get to today, but we will follow up if you submitted a question that we did not get to. Could I stream the live viscosity model back to a Power BI dashboard or Pi Vision dashboard?
Yes, so Seeq integrates with both Power BI and Pi Vision if you wanted to export that live viscosity model to any sort of BI dashboard.
Excellent. Thanks, Nick. Thank you to both Joseph and Nick for presenting today. If you have any additional questions about Seeq or if you'd like to schedule a live demo, please email Joseph. As always, we encourage you to connect with us on social media and to visit our YouTube channel to access video tutorials. That concludes today's webinar. Thank you for attending.